So let's look at another, let's say, quick example to see whether, to get an idea about the errors induced from such integration schemes. Let's try to evaluate another integral where the exact solution may differ from the Gaussian method. So let's try to integrate or evaluate the integral minus, let's say, 3 to the power x minus x integrated over dx from -1 to +1. Let's do so. Let's evaluate this integral using 3-point Gaussian quadrature technique. I will skip some tests. I can directly write down the integral here. First, we need to substitute the x1 value, which is minus 0.77459. 3 to the power x, meaning 3 to the power minus 0.77459 minus, meaning 0.77459, which has to be multiplied by w1 value, which is 5/9. Then the second term, 3 to the power 0, because now x2 is 0, minus 0, which has to be multiplied by w2, corresponds to 8/9. The third term, x3 term, 3 to the power 0.77459 has to be deducted by the x3 value multiplied by the w3 value. If you evaluate this integral, you would get 2.4229 as a result. According to, let's say, 4 significant figures, it would 2.423. So if we compare with the exact solution, if you perform this integration, if you obtain the exact solution and substitute evaluate this integral within -1 to +1, what you would end up is getting as the exact solution is, let's say, I Gaussian is equal to 2.423. I exact would yield, you see, there's an error of 2.427 minus 2.423 is equal to 0.004. See, there's in comparison to the exact solution, there's an error in certain cases. So how can we improve this error? We can increase, let's say, the number of points which we would like to evaluate increase the number of locations where which we use to evaluate the function. So we use not 3-point Gaussian quadrature. We can even go into higher number of points, 4-point Gaussian quadrature method to see whether we can improve the results. Okay. Before we move on to the Newton-Cotes numerical integration scheme, you need to keep in mind, which I will not mention here, but I will also maybe you can also refer in the additional reading material which you provided, that this integration can also be performed in 2 dimensions by integrating first with respect to one coordinate and then perform the integration with respect to other coordinates. That same applies when it goes 3 dimensions. You have to perform this integration step by step based on the variable. So you have to perform the integration for a particular variable, then move on to the other variable. Before we move on, we have to, of course, talk about this Newton-Cotes numerical integration techniques, which is also widely used in FEM simulations, but seems to be less accurate than the Gaussian numerical integration scheme. As before, we would like to evaluate a certain integral bounded by -1 to +1. And now we assume the sampling points of this yx, which is y, which is a function of x, are spaced at equal intervals. Right? In the previous Gaussian method, the Gaussian method itself selects the interval points. Of course, we give the number of intervals which we'd like to have, but the points are decided by the method itself, so that the error is minimized, or it is optimized. The selection of the points is optimized by the numerical method. But in this case, what we do is we select the space which we like to evaluate the function such that they are equally spaced at equal intervals. So this formula can be written in this way. We are discretizing now, and each, let's say, function where the equally distant interval where corresponding y value has to be evaluated, has to be multiplied by a certain, again, sort of a weight factor and number of, let's say, intervals which you like to evaluate, and has to multiply by h, the width of an interval. So we can also write this in a more expanded form, h times all right. So here the CI values are the Newton cotes constants. We call them Newton cotes constants. We perform over I number of intervals, of course, which will be less than the number of sampling points. Yeah. So if the sampling points, number of sampling points, I is the, let's say, intervals. Of course, see, this I is a variable, of course, which defines the number of intervals, or which is given by the sampling points. H is the interval between the integration limit. So for if we consider the integration between -1 to +1, then h becomes 2. If we in the case of -1 to 1, then the corresponding h value, the integration limit, becomes 2. So it's simply the width of in the x direction. Yeah. So I think you can clearly understand what is happening now. The width in the x direction now gets multiplied by certain components in the y direction, so that we try to mimic the area of the curve. So like in the Gaussian method, there's a table which gives, based on the number of intervals and number of points, of course, what are the values which we should use for, let's say, the Newton cotes constants. These are published and these are given. I will just briefly write down for sake of simplicity. So the integral is the integral which we like to evaluate from -1 to +1, which can be represented by h times summation over number of intervals, where each has to be multiplied, each y value evaluated at certain point to be multiplied by a Newton cotes constant. So based on the number of intervals, these factors will change rather. Based on number of intervals and number of points, if the number of interval is 1, of course, then the number of points are 2, then the corresponding Newton cotes constants is published such that all the others are 0. If the number of intervals is 2, then the number of points respectively becomes 1 larger than the number of intervals. Then the corresponding constants would be 1/6, 4/6, 1/6. If the number of intervals are 3, then the number of points which we have to use is 4. Then we see that we also have an additional Newton cotes constant coming into the equation, 1/8. Right. Likewise, when the number of intervals increase, there are certain factors up to C6. You can include these values, and it has been found that when using, let's say, number of intervals increase from 2 to 4, then the result seems to converge. The accuracy seems to be more or less the same. even though I have written this in this form, of course, when we increase, let's say, number of intervals in order to obtain greater accuracy, we can use smaller intervals. That means we can include more evaluations of the function to be integrated. So this can be obtained by using, let's say, higher order Newton-Cotes formula. In other words, we are increasing the number of intervals that is given by I. So based on, if you want to improve the accuracy, then you need to increase the number of samples. But at a certain point, you would see that increase in the number of points would not yield significantly improved results. So you need to select as to what is the best point to stop this this method based on the computational power, of course, which you will be using. For just to get a quick hang and just to get a feeling of for this method, let's do a quick example before we move on to discuss the three-dimensional stress elements. So assume that we are supposed to evaluate, let's say, the same integrals which we evaluated using the Gaussian quadrature method. So let's try to apply Newton-Cotes quadrature to evaluate the same integrals which we evaluated before. So the first integral is, and let's try to use this method. First try to evaluate this integral, and second, let's try to evaluate the second integral, which is from 3 times x, 3 to the power x, dx. So we can use, let's say, 3 sampling points to evaluate this integral, that is at -1, 0, and +1, which are equally distant. And we have to multiply each evaluated function by the respective Newton-Cotes constant or numbers. So if we assume three intervals, let's say 2 intervals, 3 points, we have to evaluate this function at -1, 0, and +1. And they have to be multiplied by, if there are 3 points, 1/6, 4/6, and 1/6. Yeah. They have to be multiplied with the corresponding C values, that is 1/6, 4/6, and 1/6. So the result of the integral look like 2, the length, the interval where the integration is performed. So -1, 1 minus 1 is 2. That is the length of the length in the x direction has to be multiplied by 1/6 y0 plus 4/6 y1, and again 1/6 y2. So this is the integral. So if we evaluate the first integral, y0 at x is equal to -1, y0 would be x squared plus cos x divided by 2. y0 is equal to -1 squared plus cos 1/2, of course in radian, which would yield 1.8775826. y1 correspondingly would become, you need to substitute x equal to 0, cos 0 divided by 2, which is equal to 1. Then in y2, you need to substitute x is equal to 1, where cos of 1.8775826. Yeah. So we can use the equation, the equation which we would like to use when we are using 3-point Newton-Cotes quadrature integration method. And let's try to evaluate this integral. Y is equal to 2, the length of where the integration is performed, 1/6 times 1.8 y2 value 877 y1 value, y0 value 885826 plus 4 over 6 times 1 plus 1 over 6 1.8775826, which is equal to 2.585. If you can remember, this method also provides the same results as given by the exact solution. So I exact solution is equal to, let's say, by I obtained using Newton quadrature method. But if we look at the second example, if we do evaluate the values, the y function values at these three particular points, y0 would be 3 to the power minus 1 minus 1 is equal to 4 by 3, and the y value would be, y1 value would be 3 to the power 0, where x is equal to 0, y2, that is where x value is corresponds to 1 minus 1 deal 2, and substituting to the equation general formula which we just used for evaluating the integral here for the Newton quadrature method, we would get 1 over 6 divided by times 4 by 3 plus 4 by 6 times 1 plus 1 by 6 times 2, which is equal to 2.444. Now you see there's a clear error. The error between the exact, or let's say the error between the one obtained from the Newton's quadrature method and the exact solution, the second example, is quite significant. 2.444 is the answer we got. The exact integral gives us 2.427. So you see the error is 0.017, which is quite significant. The error of, let's say, Newton quadrature method is larger than the one obtained from the Gaussian method. So this is one such example. Why, if somebody may ask what is the reason, of course you know the answer. The reason is, in this Gaussian quadrature method, the points, exact points where the integration has to be performed, or the evaluation has to be performed, are optimized in the case of Gaussian method, and it is fixed in the case of Newton quadrature method. Okay, on that note, we are done with this numerical integration method techniques. Of course, I will provide, or I will also provide some reading materials. You can also go through the reference and see how these numerical integration methods are used for evaluating higher order stiffness matrices, higher order element stiffness matrices, which are that of higher order, and how this has been used, how these techniques has been used to evaluate this integral for evaluating the stiffness matrix in different cases. So on that note, I will we can conclude the isoparametric formulation, of course, as well as Newton quadrature integration, or the integration discussion on integration techniques, and we can move on to the next section where we will be discussing about three-dimensional elements, especially used for three-dimensional stress analysis.